Hi everybody. So we're moving on to Volumes by Revolution Day 2. So everything we have done so far has been revolving these areas around some type of line, whether it's an X or Y axis or a different line, but they have been these solid shapes. So sometimes when we're trying to find the volume of a solid, though, there's a hole in the middle. So everything we did before we were referring to as disks. They were just these flat circles, and we just found all the areas and added them together. Well, now we're going to be doing stuff that has these holes in the middle. So these are referred to as washers. Okay, it almost looks like a donut, right? But there's this hole in the middle. So what we end up having to do is find the volume of the whole thing, find the volume of the little hole, and then we end up subtracting the two. So when we have a solid with a hole in the middle, we still use areas of circles. To find the volume, but we will need to take away the volume of the hole from the overall volume. So in order to do this, we have to set up two integrals. And I just want to make a note here that these can still be with respect to x or y, depending on what the actual functions are that we're dealing with. So because we're still doing areas of circles, we're going to have pi times the integral, and I'm going to make up some bounds here. I'm just going to say a to b because that's the easiest. And we're going to have capital R squared dx. Again, it could be with respect to y, depending on what we were given. But if we look here, the capital R is going to be the outer radius. So it's the radius of the big thing here, okay? And then we're going to subtract pi times the integral from a to b of little r squared dx. And little r is the inner radius. Really, it's kind of like the radius of the hole that's in the middle. All right, that's the little r. And this portion here, this volume that we're subtracting, is really the volume of the hole. That we're taking out of the center there. Okay? Now, one thing I want to point out real fast, this here, if you guys notice, they both have pi because they're both areas of circles, and they're both integrals from a to b. So sometimes you'll notice that we write it as one integral. So the volume is going to be pi times the integral from a to b of capital R squared minus little r squared, and then dx. And you'll notice both of the radii are squared separately because we're finding the volume of the whole thing, the volume of the inside, and then we're subtracting the two. All right? So let's see what some of these examples actually look like here. So find the volume of the solid of revolution formed by rotating the finite region bound by the graphs y equals the square root of x minus 1, y equals x minus 1 squared about the x-axis. So we're going to go ahead first and draw a picture of what's going on here. So I'm going to try and space it out so we can kind of see nicely what's going on here. So let's see, I'm going to go here, 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 and here. All right, well, let's see. We know that y equals the square root of x minus 1. That's just our normal square root function, but we're shifted 1 to the right. So we're at the point 1, 0. Then we're going to go over to the point 2, 1. And that's going to end up being our square root function. Sorry, I'm not at a very good angle to draw that nicely. My bad. There we go. That's a little better. Okay, and then we've got y equals x minus 1 quantity squared. Well, that's a parabola, also shifted 1 to the right. So our vertex is at the point 1, 0. And we'll go up 1 over 1, up 1 over 1 this way. And we'll have a parabola that opens up like this. And so we can see that it's this area here that we're going to be rotating. All right. Again, I tried to make it bigger for you to see, but hopefully you can kind of see what's going on here. I'm going to extend this out. I'm rotating about the x-axis, so I always kind of draw myself just a little arrow there to show that I'm going to take this area and rotate it around the x-axis that way. So if I want to try and recreate the reflection of that, that would be down here, and it's going to come this way and this way. If we rotate that, it's going to end up almost looking like a bowl, all right, when we end up rotating it. It's on its side, obviously, but it'll be kind of this bowl shape here. So we know we're finding the area of circle, which is pi r squared. And we know that since we're rotating about the x-axis, these are perpendicular to the x-axis, which means our radius is going to have to be top minus bottom. And our integral and our functions are going to have to be in terms of x. All right, so let's look at the radii here. So if we want to do capital R, that's going to be the outer radius. So if we look here, the outer radius starts right here and goes to the x-axis. So the outer radius is this function, which is the square root of x minus 1. And then the bottom function is 0. So our capital R is just the square root of x minus 1. And then for our little r, for the inner radius, if we look here, the inner radius, again, it's the radius of the hole essentially. And so we can see that there's this space in between our area and where we're rotating it. So the red piece here, that's our little r. And so again, top minus bottom, so that's going to be x minus 1 squared and then minus 0. So it's really x minus 1 squared. Okay? So if we want to find the overall volume, we know that volume is pi times the integral, and we need our bounds here. So let's see, we're going from 1 to 2. And we know it's going to be capital R squared minus lowercase r squared. And it's going to be in terms of x, so we need a dx. So again, this is our big R, and this one here is our little r, because we're using this formula right here. So little r is the square root of x minus 1. I'm sorry, that's the big R. And then the little r is x minus 1 squared. So you'll notice we actually have two squares here, because the inner radius was already squared, and then we have to square it when we put it into our formula here. So we set it all up by hand, but we're going to use our calculator to actually find the integral because it'll be faster. So we're going to do pi times math 9, and we're going from 1 to 2. And we want to make sure that we put this in correctly. So the square root of x minus 1 squared minus x minus 1 squared squared, and we're doing this in terms of x with respect to x, and so we get that our volume is 0.942. And there we go. Ooh, you can't see that. Now you can see it. We're good. All right, let's look at another example. All right, so find the volume of the solid of revolution. We've got y equals the square root of x and y equals x cubed about the y-axis. So again, I'm going to try and make this a little bit bigger so we can see really nicely what's going on here. So I'm going to put one here and one here. If I want to graph the square root of x, I know that that's going to go like this, and it's my square root function. So it goes like that. And then a cubic function I know is going to come up like this. That went a little abrupt there, but you get kind of the general idea there of what's going on. And so we can see that it's kind of this area in here, and we're going to rotate this about the y-axis. So we're rotating it this way. All right, so if we were to reflect it, we could, if we want, reflect it on over here. And again, we would kind of have this bowl shape here. Since we're rotating it about the y-axis, that right there is telling us everything needs to be in terms of y. All right, so I'm going to draw my cross sections perpendicular to my y-axis. Okay. I'm still going to need the area of a circle, which is pi r squared. And since everything is going to now have to be in terms of y instead, I know that my radius is going to be right minus left. So really quickly, what I'm going to do is this right here says y equals x, or the square root of x. We need to solve for x. So we know that that's going to give us x equals y squared. So that's actually this function here. And then for this one, in order to solve for x, we know that that's going to be the cubed root of y. So that was this one here. This is our cubed root of y. Okay, so now I need to find my outer radius. So I'm going to start in the center that I'm rotating about and go all the way to the outside area, which is right here. And so that's that cubed root of y for my right function. And my left function is, what is that called? The y-axis. And so it's 0, which means the outer radius is the cubed root of y. For our inner radius, I'm going to again start at the center that I'm rotating around and go to my graph, which is right here. That's my inner radius, and that is that square root of x, so we know that that's y squared. That's my right function, and again the left is 0, so it's y squared. And now I can just go ahead and find my volume. So the volume is going to be pi times the integral. Since everything is in terms of y, I need y values here. So this is from 0 to 1. I'm just going to make a note that those are y values because everything needs to be in terms of y here. So we're going to have our big R minus the little r, and they're both squared. So big R squared minus little r squared. It's going to be in terms of y, so that's a dy to end our integral there. The big radius was the cubed root of y, and then the outer radius is y squared. And we can go ahead and put that in our calculators. I'm going to let you guys plug it in on your own and then just check to make sure you get the same answer that I do so that we don't waste the time in the video of me plugging it in. So we get that the volume is roughly 1.257. Again, you can just go ahead and use your calculators and verify that you get the same thing. Be careful plugging in this cubed root of y. I would probably write it in your calculator as y to the 1/3 instead, just as an FYI. If you don't get 1.257 when you plug it in, it might be that you're plugging in wrong. All right? We're going to do one more. We're going to do part A, and then we'll do part B together as a class. But I want you guys to see one example of rotating about a different line. So we did rotating about the x-axis. This one was rotating about the y-axis. Now we're going to rotate about the line y equals 2. So let's go ahead and draw ourselves a picture of what's going on. We've got the square root of x, the line y equals 2, the line x equals 0. So if we want to draw a picture of what's going on here, let's see. Extend this down a little bit more. So 1 and 2. 1 and 2. Okay, so the square root of x, so that's here, here, and here. So there's our square root of x. The line y equals 2 is going to be right here. And then the line x equals 0, so that's the y-axis right here. So we can see it's kind of this region right in here that we're going to be rotating. And we're rotating it around the line y equals -2, which is a horizontal line. So what I always do is I go and I draw a dotted line around where I'm, that represents where I'm rotating. And I again draw my circle to kind of remind myself, okay, this is where I'm rotating about. So we can see there's this huge space between our area that we're rotating and the actual line of rotation here. So we need to decide whether this is going to be with respect to x or respect to y. So if we look, we're rotating around this horizontal line, which is parallel to the x-axis. So this is going to be similar to rotating around the x-axis, which means we're going to integrate with respect to x. Okay, so that means I'm going to draw my lines going this way. Okay, so now we need to find our big R and our little r. We know that the area is pi r squared. Since we're integrating with respect to x, we know the r is going to be top minus bottom. And now we just need to figure out what the big R and the little r actually are. So we are going to start here and end here. This red line that I just drew is the capital R. That's our outer radius because we're starting at our line of rotation and going to the outside of the area that we're rotating. So the capital R is top minus bottom. The top is the line y equals 2, and the bottom is the line y equals -2. So our outer radius is actually 4. Our inner radius goes from, again, where we're rotating about to the outer edge. And so this green part right here is the small r. It's the radius of that hole that we're removing from our figure. So the little r, again, top minus bottom. So that's the square root of x minus -2. And so really it's the square root of x plus 2. So if we want to find the volume there, volume is going to be pi times the integral. Let's see, we're going from 0 to 4. And we're going to have the big R squared minus little r squared. And we're integrating with respect to x, so we're going to end our integral with a dx. Capital R is 4, and our lowercase r is the square root of x plus 2. And again, you can go ahead and plug that in the calculator. I'm not going to waste the time on the video plugging it in and showing you. So plug it in and check to make sure you agree with me. I got a volume of 58.643. All right, I'm sure we have a lot of questions here, I will answer all of those when we get back into class, and we will do part B together to start class and make sure we're all on the same page. All right, I'll see you guys later. Bye.